Hi, I'm Siddhant and I'm here to give a presentation on my research work on iterative KG refinement embeddings using symbolic knowledge. This work was done in joint collaboration with Srikanta, Bedathur, Maya Ramanath, and Deepak Sharma at IIT Delhi. The motivation for our work was that knowledge graphs are often noisy and incomplete. Noise refers to various kinds of errors in knowledge graph, like incorrect relationship and incompatible entity types. While knowledge graph completion is usually addressed by learning embeddings for inferring new facts, most of the successful techniques for knowledge graph refinement perform reasoning over ontological constraints. In this work, we aim to combine the two techniques to improve performance over both tasks. The contribution of our work is to propose an iterative method to combine the ontology-based methods with embedding-based methods and show the improvement of up to 9% over the existing baselines. The block diagram of our system is shown in the slide here. The key idea is to use ontology and inference rules to produce high-quality type predictions and clean noise from the knowledge graph. In the second stage, the knowledge graph embedding methods take as input the type prediction and clean knowledge graph to produce higher quality embedding. The predictions from the embedding method are then fed back into the ontology system, which along with their scores as additional context for prediction. This feedback cycle can then be repeated for multiple iterations. PSL-KGI is one such probabilistic rule-based model that can be used in our experiments. The solution to PSL model essentially provides the most likely interpretation of the knowledge graph, which can then be used to reject noisy facts and generate new candidate facts. For more detail, please refer to the paper cited in the slide here. Now, the next block that we need in our diagram is the KG embedding. KG embedding method defines a scoring function f to score the plausibility of a triple. Recently, implicit type-supervised embeddings have been proposed that extend standard KG embeddings by representing each entity with an implicit type embedding along with the traditional vector embedding of the entity and using the scoring function mentioned in the slide. In our approach, we introduce explicit type supervision by concatenating the implicit type embeddings with the embeddings of explicit entity types and domain and range types of variation, which are transferred from the ontology system. So, to reiterate, this is what our system looks like. PSL-KGI is our ontology-based system. The X in type-E-X could be ComplEx, ConvE, or any other such embedding method. Here we show the benchmarks and their trained valid test split distribution on which we measure performance for our system. Apart from nil, none of these benchmark data sets have noise. Thus, we randomly sample 25% of the triplets and corrupt them. Moreover, we ensure that at least half of these noisy triples are type compatible, thus making it harder to detect them. This table shows the number of instances for each ontological component for different data sets. We can observe that NEL, FB15K237, and Yago 310 have rich ontology, whereas WN18RR has little ontology. Finally, to evaluate our approach, we use PSL-KGI along with the KG embeddings and ensemble methods that were created by us as baselines for our approach. In this table, we can see that our method outperforms all baselines on Yago 310 and FB15K237, whereas it is slightly worse on WN18RR because of its very limited ontology. It is also on par with PSL-KGI or NEL, which is a formidable baseline because of NEL's rich ontology. We further perform additional analysis on the impact of number of feedback iterations and different ontological constraints. We encourage you to run through these analyses. Thanks a lot for your time. If you have any questions or suggestions about our work, please let us know.